Welcome to today's lesson. I'm Siamasaka, and so today I'm going to take you through a lesson in physics, and in particular, we'll look at electric circuits. And so we go straight into the lesson for today. Well, as I indicated, today we are going to look at electric circuits. And so to simplify, in finding solutions for electric circuits or in electric circuits, Kirchhoff actually developed two rules, and these are the ones we're going to look at actually when you have a complex network of electric circuits, and so you would want to find the solution for them. And so Kirchhoff actually developed some rules, and these rules are very basic indeed, and there are only two rules. And so the first rule states that the sum of currents entering a junction must equal the sum of the currents leaving that same junction. What it means is that actually, if, for example, you have a current entering a junction and another current entering a junction, say this is current 1 and this is current 2, and then you have one current which is leaving the junction. According to the first rule, current 1 plus current 2, which are entering the junction, should be equal to current 3 leaving the junction. And so the first rule, actually what it states is that you need to sum up all the currents that are entering a junction. A junction is actually a joint in a network. And then these, the sum of the currents entering should always be equal to the sum. Also, you add all the currents leaving, all the currents actually leaving the junction. And so, therefore, this rule is known as the junction rule. It is known as the junction rule. And so, the second rule states that the sum of the potential differences across all the elements around any closed circuit loop must be 0. In other words, it indicates that you should also add all the potential differences for across each element. Across each element, you add them, and that should be in a closed circuit, meaning that you should start from somewhere and come back to the same point, meaning you are making a circle. The other ways, a loop can be, for example, starting from here, a loop can be like that. You are starting that point. So all the, for example, if here there is actually a potential difference, there is a potential difference, there is a potential difference, there is a potential difference. So from where you have started from up to when you come back to the same point, which makes a loop, you should add all the potential differences. In other words, you are adding, this is voltage 1, this is voltage 2, this is voltage 3, this is voltage 4. You add them together, and the sum of them should be equal to 0. That is actually these two basic actual rules, what they mean. In other words, actually, the rule number 1, the junction rule, which is that actually or the sum of the currents entering a junction should be equal to the sum of the currents leaving a junction. Actually, this one, it is states that a charge will never be destroyed, and therefore it means that the charge entering, in other words, if you have a junction there, you have a current coming through here and another current going out here. In other words, the charge which is entering, charge number one, and this one is entering the junction, and this one is leaving the junction. And so current 1 plus current 2 should be equal to current 3. So in other words, you are conserving here the charge. So the amount of charge entering into a junction should be equal to the amount of a charge leaving the junction. And so this is the junction rule. Similarly, the loop rule, actually, it has to do with the conserving energy. In other words, the potential difference across each element, when you add all of them, actually they should add to 0, meaning that you are conserving actually energy. And so this is what it means. And so here is a network, an electric circuit, which basically we have outlined. We have the voltage 1, and then there is the resistor 1 there, and we have the current here, and then again you have voltage 2, which is the battery there, and you have a resistor here, and there is current 2 entering to that junction, and we have a current here leaving the junction at C, and we have another resistor 3. And so we'll see how we can use these rules, that is the junction rule and the loop rule. So first of all, actually what it means is that, for example, now we have to look at the junction rule. The junction rule, as we stated, actually we are saying the current entering. So the current 1 plus current 2 should be equal to current 3. Because this current, if we take our junction, to be here at C, this is our junction. So current 1 actually is entering the junction, and current 2 is entering the junction, and current 3 is leaving the junction. And so you add the 2 currents which are entering the junction, and then the currents which are leaving the junction. So now we look at the loop rule. When you are considering the loop rule, actually there are about 4 aspects you should consider, which will enable you to actually precisely use the rule. As you remember, we said the loop rule states that all the potential differences on the loop, you need to sum them, and they should all add up to 0. In other words, for example, on this one here, the potential difference here, this is the negative part of the battery, this is the positive. And since the current is flowing in that direction, we expect that this one to be the same current from there to there. But when it reaches this point, there is a voltage drop because of the resistor. Okay, and therefore here what we're going to have is resistor 1, the voltage drop, multiplied by the current 1, which is this current here. Similarly, so we are taking this loop here, which is we are taking loop A, B, C, actually F. So this is the loop we are considering now. So in other words, what we are saying is that, again, this current, when it reaches this junction, it goes this way, and here there is the voltage 2. This is actually the negative of the battery. This is the positive. So the current will flow in that direction, and meaning that this one will be positive, and this is the negative, because there is a current is flowing in that direction, current 2 flowing in that direction. And so this resistor, there is a potential difference. This one will be at a higher potential than this one. And therefore, this is what happens. And then this current, this is for loop number 1. So when you add this voltage, this one will be positive, then this one will be negative, because actually there is a drop in the potential difference, and therefore it will be actually it will be actually R multiplied by R1 multiplied by R I1. And so this is the loop. So we'll come up with and similarly on the second loop F, we expect also the current here to go around this loop, which is loop F, C, D, E. And so here, when the current comes here, we expect that this will be positive, and then this will be negative, because the current is flowing in that direction. So basically, this is the first step we are supposed to do when actually we want to use the loop law. And so this is the explanation. If a resistor is traversed in the direction of the current, the charge in the electric circuit across the potential, electric potential across the resistor, it will be negative. What it means is that, for example, let's consider loop 1. Remember, we said loop number 1 is A, B, C, F. It is loop A, B, C, F loop. Okay, so we said that actually, if we look at the first one here, we said this will be positive V1. This one will be positive V1. Why is it V1? Because actually we are moving from a low potential to higher potential, which is from negative to positive. But when you reach on this resistor, you'll see there is a drop in the potential difference. So we are going to have negative here because of the drop. And therefore, we are going to say at this point on resistor number 1, we are going to have resistor 1, which is negative, multiplied by current 1. And then we go through this loop, we come here, and as we are going this direction now, we are going against the current. Remember this current 2 is flowing in that direction. So this one is negative, and this one is positive. So this is an increase from a lower potential to high potential. So this one will be positive. R2 multiplied by I2, meaning that is voltage. Voltage is actually the resistor times current. Resistance times current. So we have positive R2 multiplied by current number 2. And so when we reach here, now we are going towards A there. We notice that from here, we are moving from the high potential to the lower potential. So this will be minus V2. So we are going to have minus V2. And all these, they should give us actually 0. So that is for loop number 1, which we said loop ABCF. Now let's look at another loop. Another loop is actually another circle that we can make is FCDE. FCDE. We have loop FCDE, which is a loop. And so we are starting from for loop 2, we are starting from F. And so from F, you notice that if we are moving in that direction, it means that this one, we are moving from a lower potential to high potential. This one will be positive. Negative to positive, that is actually positive. So that is V2. So we have positive V2. And then when we come here, R2, it is actually plus minus. So there is a drop in potential here. This one will be negative. So we're going to have negative R2 multiplied by current number 2. And then we are moving in that direction. We come here, and from here, we are going to have, when we reach here, from positive to negative, that's a drop. Also, that one will be minus. And so we are going to have resistor number 3 multiplied by current number 3, which is going to give us 0. So this is how actually basically you can use the loop rule. In other words, what it means here, as we are indicating, we are saying if a source of electromotive force, which is the voltage, is transversed in a direction of the electromotive force, that is from negative to positive on the terminals, the charge in electric potential is actually positive. What it means is that, for example, here we were moving from negative to positive, and therefore this one becomes positive V2. However, if a source of EMF traversed in the direction opposite the EMF, that is from positive to negative on the terminals of the battery, the change in electric potential would be negative. What it means, that's how we found actually on this loop, we found V2 on loop number 1, we found V2 to be negative. It's because when we were moving in that direction, and the current was moving in that direction, which is opposite, and therefore that's why here it is actually negative. Okay. So number 1, we were saying it is actually the resistor is traversed in the direction of the current. The change in electric potential across the resistor is actually negative. If the current is flowing in the same direction as you are moving, so for example here we are traversing in the direction of the flow of current. This is the flow of current. As we are moving also, so here, this one becomes negative. However, if the resistor is traversed in the direction opposite to the current, the change in electric potential across that resistor will be positive. What it means here, for example, here, as we are moving this way for loop number 2, we note that here the current is flowing in that direction. Therefore, this one becomes negative. But in the first instance, loop 1, when we are moving, the current is moving in that direction. But as we are moving traversing, going in this direction, and therefore we are moving from negative to positive, that one becomes positive. So basically, this is actually what it means. And so we have applied the junction rule. Applying the junction rule, as we indicated, we just said actually current 1 plus current 2 gave us current 3 when we looked at the junction rule, because this, we take this junction, so the current flowing through this junction, current 1, and here the current flowing through the junction, current 2, and the current flowing away from the junction, current 3. And so that is basically what it means. Now, applying the loop rule, as we indicated, we said that actually V1, which was positive, minus R1, I1, because this is in the same direction as the current. And then we had positive R2 multiplied by current number 2, then minus V2, which is equal to 0. This is exactly what we did earlier on. We are saying here there is a rise, here there is a drop. As we come going this side, here there is a rise, and here there is a drop. And when you add all of them, they should give you actually 0. This is for loop number 1. For loop number 2, we said voltage number 2, and this one is the same direction as the current 2 multiplied by current 2, resistor 2 multiplied by current 2, and then plus resistor 3 multiplied by current 3 should be equal to 0. As we indicated, we are saying actually here there is a rise, and here there is a drop, and here there is a drop. So in other words, what we are saying here, this part here should be negative, because this is a drop also. So this is a drop also. So in other words, what we are saying here is that as we are moving from here, there is a rise, there is a drop, and there is a drop. And all of them, they should add up to 0. And so this is actually basically applying the principle of actually Kirchhoff. So if we have understood exactly what we discussed here, I'm telling you that you will not find any problems when we go into actually solving the problem. And so we need to apply this now scenario to actually the ideal question so that we know whether we have actually understood the concept. So we'll go straight into a question. And this question actually states that the first part of the question would want us to state actually Kirchhoff's laws. And then the second part is that there is actually a circuit which contains velocity and voltage 1, which is 10 volts, voltage 2, which is 5 volts, resistor 1, which is 20 volts, resistor 2, which is 2 ohms, and resistor 1, which is actually 20 ohms, resistor 3, which is 15 ohms. Okay, and so this is basically the same question that actually we are looking at. And so when you look at this one, this will be negative, this will be positive, this will be positive, and then this will be negative because the current is flowing in that direction. And if we are going to this loop here, for loop number 1, which is A, B, C, F, it means that this one will be positive, this is negative, this is negative, this is positive. And for this other loop, it means that the current here, this will be positive, and this will be negative. Okay, and so now we can merely apply the junction rule and as well as the loop rule. So for the junction rule, we know that this current here, current 1 is entering the junction, and current 2 is entering the junction, and current 3 is leaving the junction. And so to state now, the first part of the question is the state actually Kirchhoff's laws. Actually, Kirchhoff's laws, as we stated earlier on, they state as follows. The first statement is that the sum of all the currents entering a junction must equal to the sum of the currents actually leaving the junction. The second part is that the sum of all the potential differences across all the elements around the circuit, around a closed circuit loop, must be added, and they should give us actually 0. And so now we solve the question. So we said current 1 junction loop plus current 2 should be equal to current actually 3. This is the first part of the equation. And so we can say this is our equation number 1. Now we apply the loop rule. We have actually the first part of the equation is 10 volts, and that is positive. So we're going to have 10 volts minus actually 20 ohms multiplied by current 1. So we're going to have 20 ohms multiplied by current 1. Then we are going to have, this will be positive now, 2 ohms multiplied by current 2. We are going this way, to be plus 2 ohms multiplied by current 2 and minus, actually when you are going from here to there, it's minus 5 volts. Minus 5 volts. This should be equal to 0. We can simplify this equation. 10 minus 5, actually it is 5 minus 20i 1 plus 2i2, which is equal to 0. Can further simplify this equation? You can say 20 minus i1 plus 2i2, current 2, is equal to negative 5. If we bring the 5 this side. So we can avoid here dealing with the negatives. We can divide by negative 1 everywhere. And what we are going to have is 20 I1. When you divide negative, 20 divided by negative 1, you get actually positive. And then this one becomes a negative, because we're going to say positive 2i divided by negative 1, which gives us negative, is equal to 5 when you divide this one also. So this one becomes our equation number 2. That is for that loop. Now we look at the second loop. The second loop, as we can see, it will be positive 5. We are looking at loop F, C. We're going to look at loop F, C, D, E. And therefore, if we are starting from here, from negative to positive, this is actually positive, and this one will be negative. So, and this one will be also negative. And so we have 5 and 2. So we are going to have 5 volts, which is positive, minus 2 times current 2, minus, we can look at, this is 15 ohms times current 3. 15 ohms, which is negative, times current 3, which should give us 0. We are done with that loop. And therefore, we can do as we did. We can have here to simplify this equation further. Minus 15 I3, which should be equal to negative 5. We can actually avoid dealing with the negatives. We can divide by negative 1 everywhere. And we are going to have 2 times current 2 plus 15 plus current 3, which is equal to 5. And this is our equation number 3. And so now we have 3 equations. We have equation 1, which is I1 plus I2 equal to I3. Current 1 plus current 2 equal to current 3. And the second equation is 20 times current 1 minus 2 times current 2 equal to 5. The third one is current 2 multiplied by 2 plus 15 multiplied by current 3 is equal to 5. So we have these three equations. So our physics finished here. All we are now applying is mathematics to solve these three equations. So we can start from here. What we can do is that we need to remain with the two simultaneous equations, which will be easier to handle. And so we can reduce these three equations into two equations. So, for example, if we have current 2 here plus 15 multiplied by current 3. Remember, current 3 here, we found that current 3 is equal to current 1 plus current 2. So where there is current 3, we can substitute actually. Where there is current 3 here, we can put current 1 plus current 2. Why? Because we said current 1 plus current 2 from equation 1 is equal to actually current 3. So it's equal to 5. So we can simplify this equation, which is 2i2 plus 15i1 plus 15i2, which is equal to 5. We can actually add the i1. Here we have two common i2. We have 2i2 and 15i2, which gives us 17. So we can say 15i1 plus 15 plus 2, this gives us 17 I2, because we have these two, which is equal to 5. And this one becomes our equation number 4. And so now, if you note that here, we have two variables, I1 and I2 in equation 4, as well as in equation 2, we have I1 and I2. And meaning that these two equations actually, we can solve them simultaneously. And so let's solve these equations so that we can solve for I1 and I2. And so the first equation is that equation 2 is 20I1 20I1 minus 2I2 is equal to 5. That is equation number 2. Then we go to equation number 4, 15I1 plus 17I2. We have 15I1 plus 17I2, which gives us 5. So we have these two simultaneous equations, which we can now solve. So for us to solve these equations, it means that one of them should be made to be 0. So we can multiply by a factor so that we make one of these to be 0, we eliminate it. So for example, if we multiply by -3 here, multiplied by 20 to give us -60. And we should also make this 15 to be 60, positive 60, so that when we subtract, it gives us 0. And here we can multiply by +4. Okay, meaning that we are multiplying with everything here. This is our 15. And so when we multiply 3 multiplied by 20, we are actually getting -60. 20 multiplied by -3, which is I1, and negative that, -3 times -2, I2, it gives us actually 6, positive 6, I2, which is equal to negative, actually, 15, which gives us negative 15. And when we multiply 4 times 15, it gives us positive 60 I1, plus 4 times 17, that is 8. 4 times 7 is 8. This gives us 68, positive 68 multiplied by I2, which is equal to 4 times 5, which is positive 20. So we can add. If we add this one becomes 0. If you add 6 plus 68, this gives us actually I2 here, which is, this is 14. It gives us 74. I2 is equal to negative 15 plus 20. When you add this, it gives us actually 5, positive 5. And therefore, we can say 74 I2 is equal to 5. We can divide here by 74, and there 74. What we get is I2, because this one and this one will cancel, is equal to 5 divided by 74, which is actually 0.0676 amps. So it means that we have calculated the value of I2. And so for us to calculate the value of I1, we can substitute in one of these equations. For example, we can get equation number 1. We can get this equation, 20I1 minus 2I2 is equal to 5. We substitute this current. We can substitute this current there. It means that we'll be able to get I1. And so we have the equation 20I1 minus 2I2 is equal to 5. And so we have 20I1 minus 2 times 0.0676 amps, which we got, should be equal to 5. So we can say 20I1 is equal to, when you add this, you multiply this one and then you add it, it will give you 5.1352. You can divide here by 20 and there divide. So your I1 will be equal to 0.2567 amps. So we have found our I1 to be that value. And so for us to find the I2, I3, we merely use equation number 1. Since we have found this one, You have found that one. You can just add them and then you'll be able to get I3. And so you can say I1 plus I2 gives us current 3. And this one we found 0.0676 amps plus current 2. We found that it is actually 0.2567 6, which can give us actually current 3. And when you add this, you find that your current 3 is actually 0.3243 6 amps, or you can easily round it off to 3 decimal places, which is actually 0.324 amps. Okay, and so I thought today we'll look at how we can use actually Kirchhoff's law. And so this is basically how we use Kirchhoff's law. So those who want to contact me and they want to actually intensive lessons, you can contact me on my WhatsApp number, which is plus 260 97 actually yeah, plus 260 77 419949. I normally also conduct lessons which are actually live lessons where you as a student, we can actually be online actually as I take you through the lessons, and you can actually get clarifications so that I can explain exactly what actually we needed to do. You can also contact me. All these are small cases through my email, which is Siamasaka at gmail.com if you want actually one-on-one lessons worldwide. So actually I'm available, so we can arrange for a time as well as a small token that you are supposed to pay to enable you to get more knowledge. And you know, these YouTube lessons I've uploaded, I just normally look at only one lesson, but when we make arrangements, I can explain further and also actually tailor the lesson according to the course outline that you have been given. So I thank you. I hope you subscribe to my YouTube. Thank you for listening.